All right, so suppose that I wanted to determine one plus I root 3 to the 7th power. Well, I mean, we could use the binomial expansion, but that would be a mess. All right, the coefficients would be annoying. We would have powers of the square root of 3. We'd have i's taken to powers, and that gives us minus signs that we can trip over and make all kinds of mistakes with. All right, it's much better for us to use the polar or exponential form. So the way we're going to do this is we're going to say the modulus of this number is 2, and then we're going to graph where it is in the complex plane. It obviously, 1 over square root of 3 up, this is a 60-degree angle. So that means that this number is 2 cis pi over 3. All right, now as we saw on Tuesday, cis theta is equal to e to the I theta. Okay? So that means that I could write this as 2 e to the I pi over 3 to the 7th power. Well, that's equal to 2 to the 7th times e to the I 7 pi over 3. Now, from this relationship, we can see that cis of 2 pi is equal to e to the I 2 pi. But cosine and sine both have a period of 2 pi. That means that this must also equal cis of 0, which is 1. All right? So what we find here is that unlike the situation with real numbers, the exponential function is not one-to-one in the complex plane. All right? In fact, there are infinitely many values of z for which e to the z equals 1. All right, and 1 is not special in that sense. Every single number in the whole complex plane, except one number, is equal to e to the z for an infinite number of different values of z. All right? The only number that e to the z never equals anywhere in the whole complex plane is 0. E to the z is never equal to 0, but it's equal to every other complex number an infinite number of times. All right, so we're going to have to be careful with that when we define the complex logarithm. And we'll see that going forward. But for right now, I can split this up and make this 2 to the 7th times e to the I 6 pi over 3, which is e to the I 2 pi. So that's not going to bother the answer. So it'll just be e to the I pi over 3. So that's going to be 2 to the 7th times the cosine of pi over 3 plus I times the sine of pi over 3, or 64 plus 64i root 3. All right, Now that took us a while because I was explaining it the whole time. But if you look at what we did, it wasn't that hard. It's much, much, much easier than it would be to use the binomial expansion to determine this power. Okay? It is for this reason that multiplication, division, and taking powers are easier to do in the polar or exponential notation than they are in Cartesian. All right? We can also do fractional powers using our polar form. But we have to be a bit careful about that. All right, so let's suppose that I wanted to determine negative the square root of 3 plus I to the 1/2. All right? Well, once again, the modulus is 2. So all I need to do is locate it in the complex plane. Minus root 3 and then plus I is going to be over here making a 30-degree angle. All right? So this could be understood as 2 e to the I 5 pi over 6 to the 1/2. And that's equal to the square root of 2 times e to the I 5 pi over 12. All right? Which is the square root of 2 cosine 5 pi over 12 plus I sine of 5 pi over 12. And we could work out what those cosines and sines are if we had more time. But somebody else could come along and say, well, I'm not going to view this as 5 pi over 6. I'm going to view it instead as negative 7 pi over 6. Oh, okay. Well, I mean, cis of negative 7 pi over 6 is the same as cis of 5 pi over 6. So they're not wrong. Maybe they're a little bit weird, but they're not wrong. Okay? So let's see what they would get. Well, I mean, it's the same modulus, e to the minus I 7 pi over 6 to the 1/2, square root of 2, e to the minus I, and then it's going to be 7 pi over 12. This is a little bit of a problem. I might not want to work out what the cosine and sine of 5 pi over 12 and 7 pi over 12 are. You can with the half angle identity, but it's not illuminating, at least not right now. However, we can certainly look at where those numbers are in the complex plane. 5 pi over 12 is a little bit less than pi over 2. So 5 pi over 12 is maybe here. Negative 7 pi over 12 is negative, so I've got to go clockwise from the positive real axis. And 7 pi over 12 is a little bit bigger than pi over 2. So it's going to be down here. In fact, it's going to be exactly opposite 5 pi over 12. All right? And that means that this is exactly the negative of this. Now that's not surprising, because we've known for a long time that if somebody tells you x squared is equal to 9, then x is plus or minus 3. Okay, there are two solutions to that equation. So here, what this polar representation is doing is it's allowing us to get both of the numbers that would satisfy z squared equals negative root 3 plus I, all right, just by using a different argument for the thing that we're taking the power of. All right, these numbers are the same, but when I do this power, this non-integer power, I get different answers out. All right? Now, as you know, the question x squared equals 9 has two answers, but the question what is the square root of 9 only has one. All right, the square root of 9 is 3. It's not negative 3, even though negative 3 squared does equal 9. Okay, and that has to do with a convention, an agreement that everybody has come to, that this symbol should only give the unique positive number satisfying, x squared equals. All right? So we have a similar convention here. It's called a principal value. And we already learned about that with the argument. Hey, that's where these different values came from. They came from the argument. All right? So all of the principal branches of functions that are multi-valued, like these roots, and as we're going to see, like the logarithm, all of the principal branches of those functions are going to be defined by using the principal argument. In this case, of course, the principal argument is 5 pi over 6 because it lies between negative pi and pi. All right? If I wanted to deal the principal value of this, all right, I would need to use, oh, this is not a 6. Oh, wait, yes, it is. Okay, all right. I would need to use the argument that lies between negative pi and pi. So negative root 3 minus I, that's down like that, right? So I would have to use negative 5 pi over 6. If I used 7 pi over 6, I would get a different value. I wouldn't get the principal value of this number. And of course, this is going to be square root of 2 e to the minus I 5 pi over 12. All right? Now, other roots work like that as well. All right? So what if I wanted all of the values of I to the 1/3? All right, so here I'm not asking for the principal value, I'm asking for all of them. Okay? And then I'm going to say, and identify which is the principal value. All right? So let's look. I, of course, is there. It has modulus 1. All right? Its argument is pi over 2. However, I could multiply that by 1 without changing its value. That 1, however, can change the value of the root, right? Depending on the form of 1 that we use. So I'm going to multiply by the most general form, exponential form of 1, which is e to the I 2 pi n, with n an integer. All right? So I to the 1/3 would be equal to e to the I pi over 6 plus 2 pi n over 3 I. So that's cis of pi over 6 plus 2 pi n over 3, where n can be any integer. All right, this 2 pi n represents a whole number of times going all the way around the circle. All right, so I could just start here and go pi over 2, or I could go all the way around the circle and then pi over 2. That would be n equals 1. Or I could go all the way around the circle twice and then go to pi over 2. That would be n equals 2, and so on and so forth. Now we can work out what these numbers are, but it's easier and it gives us a little more insight into how this works. It's easier for us to just think about the angles. So, cis pi over 6, well, that's here. Okay? Now I'm going to add 2 pi over 3. All right? 2 pi over 3. 2 pi is the whole circle. So 2 pi over 3 is 1/3 of the circle. So if I start here and I add 1/3 of the circle, then it'll bring me over there. All right? And then if I add 1/3 of the circle again, it'll bring me here. Okay? So this is n equals 0, n equals 1, n equals 2. Now what about n equals 3? Well, n equals 3 will see me adding 2 pi times 3 over 3. But that's just 2 pi. So that means that 2 pi, or that when n equals 3, it just brings me back to 0. All right, so what looks like originally might give us an infinite number of different roots, we see here that there's only 3 roots. And of course, that's directly associated with the fact that I was taking the cube root. The denominator of my power was 3. All right, and so then that's going to lead to there being exactly 3 different values. All right? Now, of course, if you were to connect these, you would find that you get an equilateral triangle. All right, and that same thing is going to happen for any root. If I did the 5th roots and I plotted all of them in the plane, then I would get a regular pentagon. They would lie at the vertices of a regular pentagon whose center was at the origin. All right, if I did all the 6 roots, regular hexagon, so on and so forth. All right, so now which one of these gives us the principal choice? Well, the principal choice is going to be the one that uses an argument between negative pi and pi. And of course, that's this one with n equals 0. The principal value is cis pi over 6, which is that root 3 over 2 plus I over 2. Interestingly, the principal choice for negative numbers is not the one that your calculator has been programmed to give you. All right, if I ask a Texas Instruments calculator the value of -8 to the 1/3, it would give me -2. But let's see what the principal choice would be. -8 to the 1/3, so that's going to be 8 e to the, all right, now let's think about this. It's on the negative real axis. So that means that its argument is pi, 180 degrees. So I would have e to the I pi, and then e to the I 2n pi. Okay? So this is going to be 8 to the 1/3. When I write just an ordinary positive real number to the 1/3, all right, I'm always going to get the ordinary root. Okay? All the other stuff associated with complex business is going to be handled explicitly in this phase. All right? By the way, just terminology, e to the I theta is called a phase factor. All right, it just rotates a number around in the plane. So we're going to deal with those phases explicitly. So I've got 8 to the 1/3, and then e to the I pi over 3, e to the I 2n pi. over 3. All right? So once again, I would do exactly the same thing that we did here. E to the I pi over 3, that's right there, 60 degrees. All right? Now I'm going to add a third of the circle over and over again. Once again, equilateral triangle. All right? But the principal choice is 2 times cis pi over 3, which is 1 plus I root 3. All right? That's the principal value of -8 to the 1/3. If I wanted to get just -2, I would need to use n equals 1. I would have to go around the whole circle first and then across to the negative real axis.